In this video lesson, we are going to look at the use of conservation of charge, baryon number and lepton number to predict possible interactions and also to test the viability of proposed interactions that involve elementary particles. So we're now going to consider conservation laws in particle interactions, and in particular we're going to look at the conservation of charge, baryon number and lepton number, which are normally conserved in elementary particle interactions. So when testing whether an interaction is viable or possible or not, we need to test whether the above quantities are conserved or not. For if they're not, then they're more than likely not viable. So if any one of these properties is not conserved, we say that it violates a specific conservation law. So let's consider an example. Test whether this decay is possible. We have a proton decaying into a neutron plus a positron plus an electron neutrino. And we're going to make use of this table on the right hand side. So firstly we're going to look at whether charge is conserved. So the charge of a proton is +1. The charge of a neutron is 0 because it's neutral. The charge of a positron is +1, and an electron neutrino has a 0 charge. So if we look at the left hand side, it's +1. If we add these up, we get +1. So charge is conserved in this interaction. Now looking at the baryon number, we see that a proton has a +1 baryon number, and if you recall, the neutron has a baryon number of +1. We can go and check on the table here. We can see that the baryon number is in this column, and so if we look at the hadrons, we can see here, if we go down here, there's the proton, so it'll have a baryon number of +1 and the neutron +1. So if we zoom in here, we can see that. There we go. We find them there, +1 and +1. If now we go and we look at the baryon number of a positron, remember that a positron is a lepton, as is a electron neutrino. So if we go to the leptons, we look here, we'll see that the baryon number for the electron neutrino is 0, and the baryon number for the positron is also 0. So now when we look at these values, we see that on the right hand side the baryon numbers add up to 1, and on the left hand side the baryon number is 1, so the baryon number is conserved. Now when we look at the lepton number, we know that a proton is not a lepton, neither is a neutron. So if we look at our baryons, now the lepton numbers are these columns here. This column is for the electron lepton number, this is the muon lepton number, and this is the tau lepton number. So if we go and we look down here at the baryons, we see that they have, the proton and the neutron have 0 lepton numbers. So because they are not leptons, they are baryons. But now if we go and we look at the positron and the electron neutrino, we go to the leptons and we go to the positron, we see there, if we read off this table, and I want to explicitly use this table because this is the kind of table you would get in a test or an exam, we can see that the electron lepton number is +1 for the electron, and for the positron it's -1. And if we look at the electron neutrino, it is +1. So putting these values in on the right hand side, we get that it's 0 on the left, and negative 1 plus 1 gives us 0, so the lepton number is also conserved. So we see now that all three of these quantities is conserved. And the fact that all three of these quantities is conserved then implies that this interaction is possible. And this interaction is actually known as beta plus decay, because what we get is the proton decays into a neutron and a positron, which is in actual fact a positive beta particle. Another name for it is a beta plus particle, a beta positive particle, as opposed to an electron, which is known as a beta negative particle. So this is beta plus decay. This is where a proton decays into a neutron, a positron, and an electron neutrino. This is a well-known nuclear reaction, a nuclear decay reaction, which we will look at in more detail later on in this course. So now let's consider a second example. We have a neutron and a proton interact to produce a positron and an electron antineutrino. So symbolically it's written as this. We've got the neutron plus the P plus as the proton produces a positron E plus plus the anti-electron neutrino. So is this interaction viable? Now I would like you to pause the video here, and I would like you to look at whether the charge is conserved, whether the baryon number is conserved, and whether the lepton number is conserved. And if all three are conserved, then this interaction is viable. If one of them isn't conserved, then it's not viable. So pause and try this on your own. So looking at where the charge is conserved, we see that the neutron has a 0 charge, the proton a +1, the positron a +1, and we know that neutrinos and antineutrinos have a 0 charge. So the total charge is 1 on either side, so charge is conserved. Now let's look at the baryon number. So a neutron is a baryon, so it's +1. A proton is a baryon, so it's +1. But a positron is a lepton, so it has a 0 baryon number. And a anti-electron neutrino is a lepton, so it has a 0 baryon number. And so we see that in this case 2 does not equal 0, so the baryon number is not conserved. Now, while you did not need to go and prove that the lepton number is conserved or not conserved, because only one of these quantities not being conserved implies that the reaction or the process is not viable, for the sake of practice, we look at the lepton numbers, and we know that the neutron and the proton are both baryons, so they have 0 lepton numbers. And the positron has a -1 lepton number, and the electron antineutrino has a lepton number -1, and here too we see that 0 does not equal -2, so the lepton number is also not conserved. So the fact that these quantities are not conserved, both the baryon number and the lepton number, proves that this interaction is not viable, as it violates the conservation laws of both the baryon number and the lepton number. And I just want to reiterate that only one of them needed to not be conserved in order for the viability of this process not to be viable. So here is an exercise for you to do as homework for the next lesson, and it is as follows. Are the following particle interactions viable? And there are 4 particle interactions that are provided, and you need to test that in each case. You need to test whether the charge, baryon number, and lepton number is conserved. Now, up to this point, we have been representing these interactions in very simplistic terms. Here it's a little bit different, because here we are giving you particles that are not elementary particles, and we are giving you their mass numbers and their atomic numbers, and you need to make use of those numbers in order to determine what is happening with the protons and the neutrons. You need to test whether the conservation laws hold true. So this one you're going to find a little bit tough, but it's good practice for you, and you will be given the solutions in the next lesson.